So now we're going to take a look at the formal definition of what it means for a function to be continuous at a particular point. You know the informal definition of being continuous, the whole can you trace out the thing without picking up your pencil idea, but we need to be a little bit more precise than that. Let's say I want to be continuous at a particular point over here. Well, whatever I approach from the left has got to equal whatever I approach from the right has got to equal the value of the function right there. And actually, that's our definition. For a function to be continuous at x equals c, for a function to be continuous at x equals c, the following three things must all be equal. The limit as x approaches c from the left of the function must equal f of c, must equal the limit as x approaches c from the right of the function. All three must be defined and equal. The limit as we approach c from the left must equal the value f of c, must equal the limit as we approach c from the right. There is another way we can sometimes think about this, which might be easier in some situations. We could also say the limit as x approaches c of f of x has to equal f of c. If we have a limit, it has to equal the value of the function right there. We have a limit, and it's the same as the value of the function right there. And again, all three of these must be defined, and they must be equal. One thing you're going to be asked to do is if I give you a function that's discontinuous, you need to explain why it is discontinuous, basically explaining what part of this definition doesn't hold. So I'm going to give you three examples of this. Let's see. Let me take a function that looks like this. You will want to copy these down, like everything else. And I think it should be pretty clear that that function is not continuous at x equals c. Not continuous at x equals c, but we need the reason. Well, I said that all three of these things have to be defined and equal. I think one of those things is not equal. I think f of c, not equal, not defined. I think f of c is not defined. We're not continuous at x equals c because f of c is not defined. That's the part of the definition that I broke. Next example. Let's take a look at a graph that looks like this. A, B. Okay, so I've got something like this. I'm going to fill that in so I don't have my not defined problem anymore. There we go. Again, though, I hope you realize we're not continuous at x equals c. The problem here is if you look at this three-part equality, these two things, sure, they're equal. The limit as we approach c from the left equals f of c, but they don't equal the limit as we approach c from the right. I'm going to say we're not continuous because the limit as x approaches c from the left of f of x does not equal the limit as x approaches c from the right of f of x. That's my problem over there. F of c exists, but it doesn't equal the limit from the right, and the limit from the right also doesn't equal the limit from the left. Let's take a look at one more. I am not continuous at x equals c because the limit from the left does equal the limit from the right. F of c is defined. Problem is, the limit from the left and the limit from the right are not the same as the value of the function there. I'm going to say that this issue is because the limit as x approaches c of the function does not equal f of c. You will be asked in the homework to explain formally why certain graphs are discontinuous at a particular place. These are the explanations that I'm looking for, not something about a hole or a jump or things like that. Well, now that we've kind of seen the definition, there are two specific types of discontinuities that we need to be able to distinguish between. Discontinuities called removable and non-removable. Two types of discontinuities. Our first is called removable, which really is a fancy word for a hole. The idea is our function can be patched or redefined at x equals c to make it continuous. We can remove our discontinuity. Our function can be patched, or maybe a better term is redefined, at x equals c to make it continuous. For example, in this first case, I could make this function continuous by just kind of redefining my function by filling in that hole. In this example, I could make this function continuous by taking this closed dot and moving it down there, just redefining my function at one particular x value. This one, not so much. Even if I change this particular y value, I'm still going to have a jump over there. It's not going to work. This first case is an example of something that is removable. The last case is an example of something that is removable. And really what we're looking for is for the limit as x approaches c of the function to exist, but just to not equal the value of the function right there. All we have to do is change the value of the function to equal the value of the limit, and we'll be continuous. Those are removable discontinuities. Then we have what we call non-removable discontinuities. These are going to be jumps and asymptotes. Our function won't be able to be fixed at just one particular point. What I guess we need to know is that the limit as x approaches c of our function does not exist. So we wouldn't be able to redefine it at one particular point. I would say what's going on over here is a non-removable discontinuity. In the next two videos, we're going to talk about how to find particular discontinuities. Actually, why don't I do one more thing? So these are the two different types of discontinuities. There are two places we're going to be looking for these discontinuities. Discontinuities can occur when we're looking at a formula, either where a denominator equals 0, or at the end of a piece of a piecewise function. And in the next video, maybe the next two videos, haven't decided how I'm going to break it up yet, we're going to take a look at these two cases and try to find specific discontinuities by looking at the formula.